All right, guys, I'm going to try and get this one done fairly quickly. You all just left, but the Mexican potluck is happening, and I need to get my stuff upstairs and ready to go. But I want to make sure get this video done for you all for the weekend. Um, so what we're going to do today with this video is talk real quickly about depth perception. Yeah, we can see things, but how do we know that? How do I know that my door is in front of the hallway or this desk is in front of that desk? How do our brains do that? And so we're going to talk a little bit about depth perception and how we perceive things like that. First thing I want to mention is the visual cliff experiment. So there's a question, is there a thing that causes babies or small animals or whatever to know not to walk off a cliff? So they created what is essentially the visual cliff experiment, and they took and put babies on a glass table top and had a pattern here and then a pattern down here, and the hope was that the baby, although they would see a pattern all the way through, that they would actually not go as far out onto the glass because that would mean that they would fall. What they found was that all species tested can perceive and avoid a sharp drop by the time they take independent locomotion. So by the time they can move around by themselves, which is generally around 6 months in kids, they can perceive depth enough to where they just don't fall off. So this is something that develops as kids get older. And this is also among most other species that have independent locomotion, meaning they can move. Once they get to that point, they have already developed depth perception to where they're not going to fall off something. So, the question becomes, do they have to have depth perception before they can move around, or, how does that work? So, the human visual system interprets depth in sensed images using both psychological and physiological cues. Some of those are binocular, bi meaning two, ocular meaning eye, and some of them are monocular, meaning you only need one eye to do that. And that's what we're going to talk about first, is the monocular cues. All right, this is information that we get from one eye. We can use one eye to determine these monocular cues, or this depth perception. And the first one I want to talk about is relative size. It essentially, the smaller image of the two objects of the same size appears further away. And to us this kind of makes sense, but you can't just say it's common sense when you're writing scientific things. So you've got to, write it out. And so here's an example of this. These are all the ones we're going to go through. I'm just not going to go through them at the moment. So with relative size, here's an example of that. The woman, this person, and this person are all the same size, generally the same size, probably 5'8". All right, but the woman is real big, this dude is smaller, and the cop is really small. So now we subconsciously, or we already know that this cop is not growing out of this woman's head. The cop is farther away. Same thing here. All right, we know these two men who are relatively the same size. All right, we know that he is further away because he's smaller. All right, if we put him essentially at the same spot, this doesn't make sense. Okay, but this does. So if two things are the same size and one appears smaller, generally that means that thing is further away. So that is, again, relative size. All right. The second thing is interposition. And in interposition, the closer object blocks the object that's further away. So, and here is an example of that. The closer trees are blocking the trees that are further away. This is interposition. When one object appears to block the view of another, we assume that the blocking object is in position between our eyes and the block object. Now this here obviously is a little strange illusion. All right, because you would expect to see the horse on the other side of the trees, not over top of the trees. So, but this is, if you think about it like that, then there you have a column here, a column here, and a column here. So, but interposition suggests that the closer thing blocks the view of the further thing, which again is kind of common sense. The next monocular cue is relative clarity, and I don't have a good example of this. I do on my computer, actually at school, but that computer doesn't have the program I'm using to make this video, so I've got to use my laptop. All right, but in relative clarity, hazy objects seem as more distant. So here is a bad example because there's not a lot of haziness. Maybe it gets a little hazy as it gets further away. All right. A better example is probably here. If you just go to a search engine and type in hazy mountains. Maybe. And images. You'll get all kinds of images. See how the further they are away, the hazier they become in any of these. So, and that is the relative clarity. Okay, relative clarity. So the next one I want to talk about is texture. All right. And when you're looking at texture, things that are coarse, things that you can see real all the texture is think of as being close. But when something is really fine, then we see that as distant. So here's an example of that. All right. The line on the plane is seen as very fine, and we know that it's further away, whereas the bricks here on the building, they have a coarse texture. We know that they're closer. So we compare the two in our minds real quick, and that this is what it is. So this is the fine, this is the clarity, and again, that deals with texture. We use texture. The next monocular cue, again, these are all things that we can see with the information that uses one eye, is relative height. We perceive higher objects as being further away. And again, this is not a very good, but if we are looking here, all right, and we're moving down the road, things that are higher we think of as being farther away. And so, if we're looking here, we know stuff up here is further away. That is called relative height. The next thing is relative motion. And this is the phenomenon that I remember noticing as a small kid looking out the window, driving down the interstate. All right, and essentially it says as we move, objects at different distances change their relative position in our visual image. So essentially, relative to where we're looking and moving to, the things that are closest to us seem to be moving a lot faster than the things that are moving further away. I don't have a good example of that because it's hard to do that on a two-dimensional screen. But think about it. Next time you're a passenger in a car, look straight out the window. If you look down, the shoulder of the road is moving by really, really fast. Or if you look straight out, the horizon is moving really, really slow. All right, that is a relative phenomenon because it's all relative to you and from where you're viewing. So, but relative motion, as we move, the objects that are closer to us we perceive them to move faster than the objects that are further away. Of course, that's relative to us. We're the ones that's actually moving. So relative motion. And then the last one is the next one, is linear perspective. That is this one, actually. Next, hold on. Yeah. It's kind of out of order a little bit. But next one is linear perspective. And this is where things... let me go ahead and write it down. The converging of parallel lines indicates greater distance, as in looking down a road. So if you're looking down the road, you can kind of see these lines are going to converge at some point here, and this line is going to converge at some point here. All right, these two bars are the same. This one looks smaller because it's closer. All right, same thing here. These are actually the same lines. These lines are all going to converge at one point. All right, but this is how we perceive depth. Linear perspective. And then the last one is light and shadow. Dimmer objects seem more distant. All right, so here you've got a dim hole. All right, you've got lights out here, and everything gets dimmer, 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 dimmer. All right. This is actually a painting that somebody has put there, because as you see, there is the Roadrunner. This is actually a wall, but this gives the illusion, enough of illusion, that somebody actually pulled in there. So they had to paint over it. So, but that is, they're using light and shadow to show depth. So again, these are all monocular cues. Now here are some examples of some of these cues in action, and of how we can sort of trick our minds, or how our minds get tricked. I think it's kind of neat. What type of monocular cues are we using with these? I think this one was parallel lines. I'll let you all. What about this one? I'll let you all think about it. What monocular cue do we use in this picture? Which one of these did we use? All right, and then this one. I don't know if this one will work or not. It didn't work very well in the last time I watched this. Yeah, it is. And the next one. Now this is the one that isn't working. I'm going to fast forward it. It's a big glass of wine. Again, which one was used? And then in this one, this is easy. This is parallel, or the lines. Kind of neat, huh? So now, what we're going to talk about now are binocular cues. These are cues that come from both eyes, that you need both eyes in depth perception. And how this happens is that we have retinal disparity. Basically, the images differ. You get two different views from each eye, and the closer you are to that thing, that you're looking at, the bigger the disparity. And a good way to do that is to use your finger. All right, take your finger out here. All right, and kind of open one eye and then close it, and you'll notice that it moves. Finger goes, okay, that is retinal disparity. All right, and as it gets closer, the change has got bigger change. Now, what's interesting here is that I've got the computer in the background. Now, my finger is changing positions, but my computer is not because it is farther away. So the closer the things are, the bigger the retinal disparity, the more the two images will differ. And our brain sort of puts everything together. Yeah, that's what we just did. In binocular convergence, when you look at an object that is closer than 25 feet, your eyes must converge on the object to perceive it as a single object clearly in focus. So anything 25 feet away, my eyes have to come together. I've got to converge on that for me to see it as one. If not, then you'll get a type of double. You'll see it as double. So something like this, something very close. And this is an example of that divergent or that retinal disparity. So put them all together. All right, so that's really all I've got for depth perception. There are questions on the AP exam on these binocular cues. So make sure you really understand them. If you got questions about them, you can email me or you can bring them to class on Monday. Hope you all have a good weekend. I will probably do a second video this evening. I haven't decided if I want to do the video over hearing and then do the hearing experiment things in class or do everything at once because it's sort of embedded in the PowerPoint. I'll think about it, but hope you all have a good weekend, and we'll talk to you later. Peace out. Well, what's going on?